I teach math. In fact, I actually teach a lot of people who teach math.
Okay.
So that's crazy, isn't it?
I will be by you.
You will? All right. Oh, my fifth grader read all of these up to this summer. Which one are you on? The Goblet of Fire? And then I watched the movies. Is that 4?
She's not allowed to watch movies until she reads the books.
Well, he didn't either. He didn't want to, but we read it, or he read it. I wasn't reading them all, and then we watched the movies. Wow, do you like them? Yeah. Let's see, the Goblet of Fire. I don't remember what happened in that one. I don't want to give anything away.
I haven't read any.
So I don't want to tell you there, but.
She took off on them.
Just try not to hit that, because otherwise it'll knock over, and yeah. So maybe I'll try to move it up a little bit here.
I'm a math person.
You like math? You do like math? Good.
I'm listening.
All right. Okay. I don't know, Christian. You might know he commutes too, but that's just from Belfast. It's actually a lot easier south. You guys in this area have no problem. So okay. Today, still appreciating you study history, math as always. I'm going to hopefully you'll be able to follow and explain some methods of solving problems using ancient times. I've got one that we're going to look at today, and then possibly for some of your little first kind of projects or presentations that you're going to do, get together with somebody and maybe even come up with, you don't have to come up with a problem or a solution method or anything, but maybe that's something that has interested you as you've been doing your research and studying. And maybe you'll say, I want to delve into that a little bit more, and maybe you'll present something, because that's kind of your homework. So, and then we'll finish up prior to 600 today, and explain what was happening mathematically during that time period, and explain some major mathematical figures if there were. And I do want us to try to make some personal connections between today and history, considering ways that history affects today. For instance, I was thinking about, I was trying to think and reflect about what happened or what I did the previous class period, and one of the things, because I wasn't necessarily prepared to talk about it in any detail, was our brief digression and talking about the difference between a system that is just base oriented, and I'll just say oriented, versus positional. Okay, positional system. So when I say something is base-oriented, all that means is it's grouped by the base, okay? And if I asked, I won't put them on the spot, but if I asked our elementary students, visitors today, if I said, in school, when you have groups of objects, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, like that, we group by sets of what? Answers over there. How many of these would I group together?
5.
I might group this end by 5, but in our number system, we group by sets of, in the number 234, this is the ones column, and this is the what? What column?
Tens.
Ones column, tens column. See, I got them answering before you guys. Tens column. So what we do is we group by sets. We group by sets of 10, right? So when I say something is a base system, and you might be reading a little bit about this, come up with a base system. They didn't have our numerals. They didn't have, when I say numerals, that's a numeral. Okay, not a number. That thing right there, that's not a number. Okay, one of your questions was the difference between a number and a numeral. Wait, you have a question back there, yes?
I know what that is.
What?
That's called the 100th place.
That's the 100th place, yes. And now think about it. It's the 100th place. It's okay, Amber. It's the one. This is what I do. It's the 100th place because we group by tens, right? Now, so in just a base system, we would group by tens, and we would say there's a symbol for 1, and then there's a symbol for 10, and then there's a symbol for 100. Okay? And then a symbol for 10 100s, 1,000. So maybe in some of your readings, and maybe somebody will want to present this on Thursday, is what system had different symbols for ones and tens and hundreds, and then that's how they would name it. The problem with that system is that if this symbol right here stood for 10 or 100 or whatever it stood for 10 or 100 or 1,000, wherever it was on the paper. Okay? That is a base system where we just change symbols every time we have a new group of the base. A new 10, a new 10 tens, a new 10, 10, 10, whatever. In our positional system, and ancient Babylonians, they had some positional stuff going on there too. So you might want to research and present that a little bit too. They did a little bit better than the Egyptians in the sense that they had position. So what I mean with position, this is something that most of you probably never thought about, okay? When we look at these, and I'm not going to call these numbers at all. Yes, I could say that's the number 3, okay? Yes, that's the number 8. But if the only thing that is a number, then this number is then 12. Because that's 8. And this is 4. And that means 12. But we know this isn't 12. We know this is what? Anybody? Not just for the children.
84.
84, right? We know this is 84. Now, why? I use the same symbol here as I might use in that number. It's the same symbol. That's why I'm not going to allow you to say these are numbers. These are symbols. We have a word for that. We might call them digits. But the real word we have for it is what? It kind of sounds like number, but it's... The Romans had it down pat, right? The Romans had it down pat because it was a Roman numeral. Okay? And in a way, they were a little smarter than we are because it's a Roman numeral. It's the Roman symbols. We call these numbers. Okay? But they're really just symbols. They're Hindu-Arabic symbols, so we're not there yet as far as history goes. But what that means is, here's the great thing about positional systems, is that I can make any number I want out of these 9 symbols, knowing that it's base 10. So I'm regrouping every 10, but I don't need a new symbol every 10. I'm going to use these symbols because now I've combined the base with the position, and I've said this. If you put that symbol, that numeral, if you put that numeral symbol here, it's 80. If you put it here, it's 8,000. Okay? Now, that's why we would then do this. And possibly not the second graders among us, but definitely the fourth graders among us have done this before. 8,231, you have said this. That 8 is 8 times 1,000. We all did that, wrote it in expanded notation, right? In fact, you didn't do that first. You wrote it like this. 8,000 plus 200 plus 30 plus 1. And then you learn to do 8 times 1,000. But now I'm invoking the base. Okay, I'm invoking the base. 2 times 100 plus 3 times the 10 plus 1. And then you took it one step further, and now it's 8 times 10 cubed. Okay? We'll do that till 5th grade. And 2 times 10 squared, plus 3 times 10 to the first, plus 1 times, then in 5th grade, I can say this. Well, if I keep the pattern, 3, 2, 1, the next obvious pattern is 0. So 10 to the 0 is what? It's 1, right? Because 1 times 1. Well, anyway, that's the difference between the base and position. A couple questions for you. Start us out with, from what 2 areas of scientific study do we get our evidence of prehistoric mathematics? Share with somebody near you, regroup or anything. Where? What 2 areas of scientific study do we get our evidence of prehistoric Prehistory just really means what? Before what? Pre meaning before. It's before writing, not before history. That's silly. Prehistory, before the writings of it, right? So what two areas? Give me one. Anyone? Spit it out. Anthropology. Give me the other one. Archaeology. Anthropology and archaeology, right? Now, here's what we don't really know, and I'm not going to sit here and say that I actually really believe this. I mean, you can talk to me or ask me. You can ask me now what I really believe. I don't care. But you know, I'm not. I know that anthropology books and even math history books, you know, might say something like this. Might say, when man first began, you know, they were just randomly walking all over the place and hunting animals. Okay, and that was their survival. And then like we've said, you know, as far as prehistory, history says they started out as agricultural, right? So then we make the argument that, okay, as it urbanized and people became agricultural, that was the societies that we have in writing. Personally, that's where it starts for me. Okay, you know, we don't really see evidence. The evidence doesn't really look like it to me. That there are, you know, that people roamed around for, you know, whatever, shooting animals and driving them around from town to town, you know, whatever. But anyway, but that's it. That's what anthropology does. All right, so we got anthropology and archaeology, but from there, remember, we really just piece crap together. Okay. Second question: as man urbanized and became agricultural, why did math need to be developed? What were some of the reasons that math needed to be developed? Go ahead and discuss. There are some reasons. I gave you a bunch of them. What were some of the reasons? Aaron, give me one.
Keep track of stuff.
Okay, keep track. What kind of stuff they need to keep track of? Sheep, maybe. Okay. Farm animals, whatever. But they're livestock. Okay, maybe that. What else?
Build levees and stuff to keep the water from.
Build levees and stuff, right? Because agriculture, right? They wanted to grow things. We got to get the water from there to here. We got to maybe stop streams and rivers from flooding. All right, how are we gonna do that? So we need some smart people who are gonna figure that out. What else? What else? Wait, you said what?
Crops.
Do what with crops?
Keep track of them.
Keep track of them and store them. Maybe. What else? And to trade, right? To go from town to town, place to places. You have this stuff, you can grow this stuff, and we'll do some trading. You say something else? Give me another one. President Trump's going to probably talk about it today at the State of the Union tonight. Not immigration. Taxes, right? Taxes. We got to compute taxes. Yeah, things like that. Good, good. Why is it difficult to piece some of this ancient history together? And not just prehistory, I'm just talking about ancient history, not prehistory, there wasn't any writings at all. But what were some of the reasons, like why is it difficult to sometimes piece some of the ancient history, and I'm talking about even with writings and that, together? Go ahead and talk for 15 seconds.
Yeah.
That question might be a little vague, but why is it a little bit hard to piece some of this together? Give me something. Why? There's something, Kate.
Because the papers and stuff that they're trying to store properly.
Okay, a lot of the times, I mean, and it's like in ancient Babylon, maybe the tablets were pretty good for that dry area, but not very good in the wetter cultures, especially bringing them over, you know, different places and that. What else? What else? Go ahead, Amber.
Different areas did it different ways.
So different areas did it different ways. They all oftentimes didn't know about each other. Yeah, and something else?
And then just a lot of it's kind of us putting it speculation.
Yeah.
What they meant with the
Yeah,
word.
we're trying to speculate. A lot of things have been destroyed, not just because of what it was written on, but because kingdoms rose and kingdoms fell, and you know, and we're doing things better than you are now, so we're going to destroy everything that you did. Little things like that. So here's an ancient problem. Start out solving. It doesn't seem so ancient because it pretty much seems like our algebra textbooks today, right? I wrote it up here because I didn't want to give you my solution method. It's not my solution method, it's up here. So it says, if 1 plum and 3 peaches weigh a total of 750 grams, and 2 plums and 1 peach weigh a total of 500 grams, how much does a single peach and a plum weigh? Now I'm going to pretend like I'm an ancient Babylonian and try to solve their method, okay? And I'm going to say something like this. So 1 plum and 3, and you can't write anything down because you don't have any paper and pencil. Walmart was not around the corner, okay? And as your teacher, I do not have a bunch of pencils up here, and you can't raise your hand and say, can I have a pencil today? Or not mine. So you know what I'm talking about.
Like children?
So, all right, here you go. If 1 plum and 3 peaches weigh a total of 750 grams, and 2 plums and 1 peach weigh a total of 500 grams, how much does a single peach and plum weigh? I'm going to say to do this, because these are on a scale, by the way. These are on a scale, okay? Double the first scale, okay? So if I double the first scale, and then subtract the second scale from it. Now you're already lost, because I'm talking rhetorically, and I'm not telling you to write it down. Fourth graders figured it out already. So, I see you're up there going, So you think about it with me, you people who've been abused by algebra. If 1 plum and 3, if 1 plum and 3 peaches weigh a total of 750 grams, I said double that. So that would mean, what would that mean? Kate, what?
2 plums, 6 peaches.
2 plums and 6 peaches, what?
Which equals 1,500.
Weigh 1,500 grams, okay? And then I'll say this. Now, subtract the contents of the second scale. It's not going to solve this problem. Subtract the contents of the second scale. So right now you have 2 plums and 6 peaches that weigh 1,500 grams. Now, maybe you see why I did that, but I say subtract now just the first scale. Subtract the 2 plums and 1 peach. Well, that's kind of convenient because when I double the first, you end up with 2 plums, right? So if I subtract the 2 plums and a peach, I'm left with how much? I'm left with 5 peaches that weigh a total of what? 1,000 pounds. 1,000 grams. Because those are some heavy peaches. 1,000 grams. Therefore, 1 peach weighs how much? If 5 weigh 1,000, 5 weigh 200, or 1 weighs 200 grams. Okay? So now if 1 peach weighs 200 grams, now take that peach away from the second scale. Seems like I'm doing a lot to, going around my back to get to my elbow. You know that phrase, right? Going around my back to my elbow instead of I could just go there. Anyway, so I don't know where I'm at. So now subtract that 1 peach that I found, which was 200 grams. Am I right? Found 1 peach, 200 grams. So now subtract that from the second scale, and you'll be left with what? 2 plums weighing how much? Well, 2 plums weighing how much? 300 grams. Therefore, a plum weighs weighs 150 grams. Therefore, how much does a single peach and a plum weigh? 200 and 150, 350, right? That's how I would do it if I was in ancient Babylon. What I want you to do right now is this. Solve the problem in our methods. And with a partner, turn around with somebody and say, well, this is how I would do this. This is how I would do it in algebra class. Okay? Get with somebody. Go ahead, solve. Quickly, shouldn't take that long. So you actually do multiply by 2, huh?
Yeah.
Well, we usually call it, I guess the official method is a linear combination method. Most people just call it the addition method. Or elimination method.
Yeah, that's what I was
elimination or addition, because you're adding 2, but there's nothing stopping you from subtracting, because if you just multiplied by 2, you have to subtract.
Yeah.
Okay, which is fine, because subtraction is just adding the opposite. But most of us, I think would probably, if I had said solve that problem at the beginning of class period, you just set up a system of equations, right? And that's what we do.
Yeah.
X plus y, let x equal the weight of the plum each, whatever, and you say x plus y equals. But pretty impressive, pretty impressive that they did that in their head, right? The next question, though, is, because it's rhetorical, right? I'm just arguing it out, and I can't write it down and keep it for record. It's just, this is it. So the question that I really want to kind of focus on there is, does the ancient rhetorical method always work? I mean, think about what they actually did and what we do today. So what I mean is, if I give another example, think about if it would work. So, and I will say this, what might have confused us right away is, even though Gary, when he wrote his x plus 3y equals 750, he went ahead and multiplied his top equation by 2, which is really what I did there, doubled it, okay? But how many people, when they solved it, they just multiplied by -2, though? Because when you add, that would be how your teacher would want you to do, because you add to cancel. Now, a lot of teachers won't even, this frustrates me about working with people in schools, is the fact that, I just say eliminate, okay, eliminate. So you can add or subtract to eliminate. It doesn't have to be the opposite so you can add. You can subtract, and when I say that to teachers, like, oh, my students can handle that. Well, no, the problem is you're stupid, rather than giving them some, sorry, I said yes word. You think your kids are not very smart when you got to give them the benefit of the doubt. But anyway, so let's look at this, just thinking about this as another example. If I said 5x plus 3y equals 16, and 3x plus 2y equals 10. Now, if we were to solve that using our methods here, we would probably do something like, and this is one of those messed up ones where you got to do something to both equations, right? But we might say, I'll multiply the top equation by -2 and the bottom one by +3, or this one by -3, this one by +5, whatever, and get one of the variables to cancel out, right? But I want you to think about this. So what if I said this? If I said rhetorically, just double the first and triple the second. Okay, that's my rhetorical way, right? I'm just saying double the first. So, because I'm not going to say multiply 1 by negative something, because I don't believe in negative numbers. I've never run into a negative number. Okay. So I have to say, multiply the first equation then, double that, and triple this one. Okay. Now, if you do that, if I double this, then I get what? 10x plus 6y equals 32. Triple that, 9x plus 6y equals 30. And then, now, we would subtract the sides, whatever. So from there, then I can say, subtract the new second from the new first. Okay? So we subtract this equation from that equation, right? Add the opposite, whatever I do. But if I subtract this from that, then this goes away, and I'm left with what it actually, of course it'll work. I'm doing the exact same thing. Sure, this is a really good method. We just algebraize it because we have a nice notation. Now, as we progress through the years, we will see weeks in here, years for chronological study. But as we progress through the years, we'll see maybe need to develop a written system with algebraic symbols to make things easier, and we can write things down in that. Yeah.
You're aware your screen says therefore 1 plumbing equals 150 grams.
Oh, no, I'm not. Wait, what does it say?
1 plumbing equals 150 grams.
1 plumbing. That's right. So I like plummies. So that's all right. Skip over that. Okay, so let's continue where we are before you guys doing something here. So thinking about, just a quick review. We talked about the little area where we're looking at go right in here, right in that little area, really only a few hundred miles apart. Talk about some of the bones that we see from prehistory, assuming that maybe they have some markings that we're counting, whatever. Talked about in the ancient Orient, what that actually means, anything really east of like Greece area. And then the first thing we talked about was the rising up of the urban societies, the need for mathematicians, why we don't often have good records. And let's see, we kind of ended, I guess we ended right there. Yeah, we ended with a couple documents, and when we see, and hopefully you're reading about this, and you'll read a little bit more maybe for a little bit better presentation on maybe the Rhineland Papyrus or Plimpton 322, something like that, for you on Thursday. What you might read is that in all of the uncoverings of ancient Babylonian, Mesopotamia area, I think the number's about 500,000 artifacts on their tablets. Okay, of those 500,000, like 400 of them are mathematical in nature. So I mean that's it. That's all we have, and most of them are this big. Okay, the biggest ones are like a textbook. And when I say textbook, I don't mean you opened it up and there were 300 more pages in there. I'm talking about that table was as big as a textbook, and that was it. Sometimes they wrote on both sides. Ooh, double sided copy. And sometimes they didn't, but that's about all they. That's all we have. It's like 400 of these little things. We don't have a lot of things. And some of them even, and I don't remember, it's not a test question or anything like that. How many questions are there? 85 on one, 26 on another. I don't remember. It's not that important. Okay, so what is more interesting? So keep in mind, I do this throughout my chronological study of our presentations of the history of math. This is kind of like the second important thing, not the second slide on ancient Orient, but the second kind of grouping of things, and then we see a 3 would be the next thing. So, ancient Babylonians, here's how they multiplied two numbers. And I know you think this is silly because we just know how to multiply. We multiply basic facts, we know them in our head, and anything else is multiplied by this really cool algorithm that we have, right? That we've learned how to carry things and put down and add things and move over. But I want you to really, really think about those methods. Those are all predicated on understanding the base 10 positional system. Okay? It's all about the base 10 positional system. Because when you do this right here, and I'll do it in an intermediate way. 7 times 2 is 14. I'm not going to do our standard algorithm. I'm going to write down 14. And when I do, I know what the algorithm forces us to do is say 7 times 3, that's 21. And how I put 21 down is all dependent on where I'm at in my process. But I want you to think about what I just talked about the positional system too. It's not 7 times 3, because that's not a 3. It's a 30. So it's 7 times 30. And that's what? 210. So I write 210 down. And if you did the same thing with these numbers here, you don't need this fancy algorithm, but you have to have some number sense. It's not 4 times 2, it's 40 times 2. So I'm not going to write 8 down, I'm going to write 80 down. Okay? Same thing with that. It's not 4 times 3, it's 40 times 30. So it's 1,200, 1,200. Write it down, and you've got your 4 intermediate steps that suck up to 2 when you do your algorithm. But they didn't have that. Okay, they didn't have that. They had these tables. And one thing we do know is that this is how they made tables. They were meticulous table makers. And one thing we know is they had tables of squares. And when you do some research, you're gonna see other kinds of tables that they had. They have tables of squares. What were the tables of squares used for? Tables of squares were used for multiplying numbers. Multiplying numbers by doing what? And you can algebraically work this out to see that this is right. You know, for us, it's like, that's a really stupid way of doing that. But they used the table of squares. Squares were important. Okay, so figure out the squares first. I mean, first of all, there's geometry to it, right? And area to it. But to multiply two numbers, if I take the squares, if I take the squares, did I say that? Yeah. If I take the two numbers first, add them and subtract them, and take their squares. So adding and subtracting, that's easy. And then I go to the squares table, and I find those numbers, and I subtract them, and then divide by 4. Okay? Now, I don't know, dividing by 4, was that deemed easier than anything else? You take half and half again, something like that. We don't know necessarily how that works. But just remember, they didn't have our traditional base 10 algorithms. They used tables to solve linear, quadratic, even cubic equations. I'll do some things for you on Thursday, too, while you guys are presenting. I'll have some things that I'd like to see us look at as well. So they use tables for it. They solved cubic equations. Now, here's the thing. Unlike us, they couldn't solve every cubic, we don't be able to solve every cubic equation, but there's a formula now that we know of for a cubic equation, but they couldn't solve every cubic equation. They could only solve some that looked a certain way. So that was actually the ultimate question as we go through medieval times. They couldn't solve everything. And when you think of quadratic equations, they even divided their quadratic equations up into different forms. So what I mean is, what do? Just make it all look like this, folks. ax squared plus bx plus c equals, and we think this is easier for students, but my goodness, for us it's easy. But for a lot of kids, it's not easy. We just do this, use the quadratic formula, maybe factor if it can, or whatever. What they did was this, they had a different method. If it was that versus that versus, and from a rhetorical, and we'll see as we go on, from a rhetorical situation, I guess, these all came from different problem types about squares and things like that. So they didn't have the quadratic formula. But you'll see that maybe they did have the quadratic formula, just not in the form that we often think about it. And they needed to be special type of numbers because they certainly weren't going to deal with certain negative numbers. And they certainly weren't going to take the square root of a negative number. Right? That imaginary stuff, they couldn't even handle irrational numbers. How the heck are you going to handle imaginary? Some of the methods, I want some of you to think about, I want to research a little bit. You don't have to understand it all. That might be something interesting. All right, third thing about the Ancient Orient. We have most of our records from the clay tablets or the papyrus, so we have most of our records, just archaeology, I guess, from Mesopotamia, Babylon versus Egypt. Okay, and when you think about these two, I don't want to call them competing, but these two societies, Babylonians seem to reach a far higher level of mathematics than the Egyptians. Why is that? They were just smarter. The reason probably is due to their numeration actually being positional. And when things are positional and we understand, so again, somebody's going to research this, okay? When we understand their symbols moved, and it was the same symbol. We didn't need to invent a new symbol just because we regrouped by 60. We can use the same symbol, but if I put it over here, if I put it to the left of this, if I put this symbol here, if I put that symbol right there to the left of, this symbol over here, then this, just like the ones column, this is how many ones, this could be a 4. And this could be a how many 60s you are, okay? See how that works? and think about how, just think about it. I'll make it even. I'll make it even. I mean, think about how much easier position makes mental arithmetic. So much easier positional makes mental arithmetic than if it was non-positional. Non-positional, I just gotta add up a bunch of the different symbols. But think about this, 23 and 47. How do we teach a kid to add 23 and 47, okay? We don't teach them at first to put 23 on top plus 47 and then do this traditional algorithm. We want to gain some number sense. And what I mean is, and I hope you grew up doing this. I didn't grow up doing this. You know, I grew up in the 70s where it was all just, you know, pounding away at algorithms. They do a very good job in elementary schools today with teaching, you know, number sense. I mean, my wife wouldn't say that she has a great number, very good mathematics, she's a finance person, but doesn't have great number sense. And with my kids going through elementary school, she's always saying, I've learned so much about, you know, just number sense and that, because when I'm teaching my, you know, well, kindergarten and fifth grader, you know this, but 23 and 47, I teach them like this. Well, think about the 7 and the 3. That's a 10, right? Okay, well, that's just another 10. And it's not 2 and 4. Your algorithm forces you to think like 2 and 4. This is 20 and 40. That's 60, and you got another 10. That's 70. Mentally. So position and base helps you out a lot in your number sense. Okay? It's one of the reasons why even today, you know, you think of a lot of Asian countries doing better than the United States on tests and that. A lot of people think that part of their and you study about this a little bit if you choose to do this. Their system of numbers, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we got these strange teen things, which every kid in the world messes up, you know, when they're learning those. 13, 14, 15. Now there's some history and inherent understanding in 13 and that, but in most Asian cultures, when you say 11, the word actually means 10 and 1. So when they count, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 and 1, 10 and 2, 10, 3. Oh my goodness. Why don't we, now you're gonna think this is weird, but why don't we count like this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 21, 22, 23, 24, 10. I mean, you think that's stupid until you get to 20 and you realize we do. 21, 22, 31, 32, right? Why not 21, 22? It's 10 and 1, 10 and 2, 10, 32 is 3 and 2, or 30 and 2, right? So why don't we do that? And there's a lot of, you know, thinking that that's one of the reasons why we don't have as good a number sense going in.
What is the history behind that? Why do we do that?
Well, I mean, if you actually think about it, like even the concept of teen, I mean, the words do mean 10. So, you know, when you say 17, I mean, that teen is 10. It's 7 and 10. The etymology of the word it's just not apparent, okay? Because it's not our language, it's coming from Latin, all right? So, you know, that's one of the reasons why the United States is the only people that actually have what we call teenagers. Now, everybody else, you know, has teenagers because we're the Western culture that, you know, is the lead culture in the world right now. But we're the reason that everybody has teenagers. Okay. Other than that, I mean, 13 in China, you wouldn't have called them a teenager. There's no word teen. Okay, we call them teenagers. Then you have teenagers now.
So the Babylonians actually had 60 symbols?
Well, no, that's not true. They had a base 60. Doesn't necessarily mean they had 60 symbols though. That just means they took their symbols and they moved them over, and then it was a 60, because they still had like a 10, and if the 10 was in the position, then it was 10 of those. So they didn't have to have 60 different symbols necessarily. It was some symbols, and then there was a 10 symbol, but then depending on where that place was too. That way, if you really wanted 13 in the 60s position, you could write it with less than the number of symbols that you would need. In there, you can still write it with a 10 and 3. You would just put that in to that 60s position. And of course, then the problem is, where is 0? Where is 0, right? So you need a 0. Well, they did have a symbol for 0, but they only used that 0 in the middle of two numbers. So you actually never knew if there was a end zero or not. You might consider that a beginning zero. But again, I want some of you to study that a little bit more and kind of present a little bit more. All right, ancient Babylonian text became strongly influenced by the development of astronomy, characterized by careful analysis of the different positions of celestial objects. You know, there's a lot to be said, and I should have brought this up. You know, we talked about music a little bit, and just the beauty of music, but that's what you can hear. There is something to be said that the ancients, very mystical, right? You know, the ancients looked up in the heavens and they saw the bodies moving. They marked them down. They were very much into astronomy, and it was something that they called the universe. Well, which one's first? Musicalis universalis, something like that in Greek. It was the music of the universe. Okay, we translate that to be the music of the spheres. So when they saw the bodies moving, I mean, it was music to them. That's weird to us because we're not a mystical, society. But there's if anybody grew up in the church, you might when I grew up singing a song, "This Is My Father's World," and the words. Pull up real quick here. It's interesting to see the words. "This is my Father's world, and to my listening ears, all nature sings, and around me rings the music of the spheres." So that phrase right there is very mathematical in nature when it comes to thinking about how the ancients thought about the heavenly bodies, and it's moved like it was music to their ears. It wasn't really making sound, but it was music to their ears. And I suppose for some people, that still study astronomy, because math is kind of like that to me. When I look at math, I'm doing math, and some of you too, right? You're like, man, I can't believe how that is awesome how that worked out. And I'm sure people that study astronomy think the same thing. That meant that mathematics became even more perfect in its computational techniques, with some even so they wanted to be perfect. They wanted to explain what was going on in the heavens. And some of them, they took it out to 17 sexagesimals. That's just the base 60. 17 places. We don't take anything out of 17 places today, right? We estimate it. They took things out to 17 places. That's how precise they wanted to be. Again, mostly with tables. Fourth thing with the ancient Orient, and this kind of leads us into the next phase, which is Greek society. Nowhere in all of Oriental mathematics do we ever find any attempt at explaining why. So even now we just why would they do it this way? We just make it up. Okay, explaining why. There's never a demonstration. Okay, it's always just do this, do that. Okay, so if you want to solve this problem, do this. Now, doubling the first doesn't always work, right? But doing something to the first, and most of their problems seem to have been repetitive in nature. We're always worried about generalizing something. We want to generalize it. For them, it's a specific problem. This is how you solve it. So double this, subtract that. It's wow, it worked. We can generalize it today. We have no idea how the theorems or methods were found. And I personally don't really care to speculate, a whole lot. You can read people and they'll say, oh, we think this and we might that. That's, people much smarter than me getting together and saying, let's just all agree that this is what, we're going to say happened. And then we'll just tell everyone else what happened. It was deeply rooted in the original problems of technology administration, from which it had been invented, and therefore it didn't care about asking the why or how question. Why does this work? Doesn't matter. It's technology. I don't mean digital technology. It's just technology. And then we think about Indian and Chinese scholars of later times. So when I say that, when we start reading about 500, 700 AD now. So when we read 700, 500 years, they would write about their history of, the way they did math, but we don't really have any evidence of that other than the fact that they say that would happen, which is fine. You know, the Chinese and Indian cultures very, you know, what's the word I'm looking for? Handing things down generation to generation. I think is the word for it, but we really don't have any evidence really before the Christian era, so BC. We do know that the ancient Hindus did use decimal base 10, so they used decimal base 10, but without place value. Okay, no place value. In the Suva Sutras, which is some Indian religious text, has parts that date back to 500 BC or earlier, contains some mathematical rules which may be of ancient origin. So, you know, again, we don't know. It's been referenced later, mostly for construction of altars and things like that. And, you know, with India being so large, there's probably different ways. We think about how big, if you go back to that, you know, map, how big India is. It's huge. And even today, we see things, you know, broken up into parts of India. And so most likely, things were done differently. You know, even today, you got the Buddhist, you know, area, you got the Jainism area, you got the Muslim area, and that's one of the sacred books. The value of pi is the square root of 10 is given. Kind of lastly there, wrap it up, Chinese classics, there's, I don't know how to pronounce this stuff, the Chu Shang Shuang Shu. It's called 9 chapters of the mathematical art, date back to 200 BC. Okay. There's another book, the I Ching, Book of Changes, in which the Lo Shi, the magic square, something a puzzle, you know, type of thing, magic squares found. A lot of legends in the magic school. When you see magic squares today, you know, that might be something that somebody wants to look into, like magic squares, where are they today and how are they computed there. So Chinese numeration has always been decimal. You know, when you study the Chinese system, you know, so they don't really do this now, but the ancient way of writing Chinese was vertically, and part of that has to do with the way they wrote. It was like on bamboo and bark, and the way they would slice the bark would come out like, I mean, I don't know why they just didn't turn it, but maybe it was easier to write on, you know, that way because of whatever, you know, is in the bark. But it ended up being longer like this, and so you see sometimes in Chinese and Japanese things are written vertically. And again, if you choose to study their symbols, you will see this. How, because it wasn't place value. How did they write 32? Well, they might write 3 10s, so how would they write 3 10s? They would write 3, the symbol for 3, below that, the symbol for 10. So it would be 3 10s, and then 2. Okay? So rather than, like us, you know, position, we put 3 over here, it automatically means 30. But again, that also precludes the fact that we have a 0 in there. You know, Chinese, again, very unbroken, so, you know, more modern times, transmitted. That's part of the word I'm looking for. Transmitted from generation to generation. Of course, whenever your society is based on transmitting generation to generation, you know, things don't, and that's all you're concerned with is learning how we did things in the past. You know, you don't grow a whole lot. So, you know, and this is where this time period ends then. So we've gone here to the ancient Orient, but it's going to take a while. It's going to take the emergence of, and grasp on this last paragraph with me, okay? It would take the emergence of an entirely new civilization to interrupt this style of mathematics transmission. Just, you learn this because this is what we do. This is how we live. An entirely new civilization. The different outlook on life, characteristic of Greek civilization. The Greeks come in, right? They overtake everything. What's their culture? That's going to bring mathematics up to the standard of a real science. The Greeks are where we get all of our logical structure from and stuff like that. So the society known as the Greeks, that's where we'll be able to start the next time we come back to more, probably next Tuesday. But we'll end here and say, you know, we've got the ancients, we got Babylonian, and what was going on then in mathematics, okay? Not a whole lot that we know. We know some of their symbols. It's interesting to look at how they, you know, did some things, but it's going to take the Greek society and Greek culture to really bring us up to where we are, you know, or the foundations, I guess, of today. So, okay, so here's what I'm going to have you do now, and I know this will be problematic for some of you. I mean, you can do things. You have 25 minutes here. You might have some time between. You might have some time if you're all, you know, here in class. Today, if you absolutely can't do things with a group of people, then you can do something entirely on your own. That's fine. But I'm going to put you into 12 people. I'm going to put you into 4 groups of 3, and I want you to do this. Here's what you're going to do. You all thought about, hopefully, some stuff. You know, hopefully you got some ideas, and I want you to continue adding to the ideas on D2L as well, so you can kind of see what's going on out there. But pick something that makes that gets you excited, or that you want to learn a little bit more into about this area or this time period prior to 600 BC. You're going to present to the class on Thursday. This isn't a formal presentation or anything like that. It's just you going up. Maybe it's a problem that you saw that was solved, you know, a cool way. Maybe it's some symbols in a certain thing or in a certain society. It could be an artifact, you know, something about Plimpton 322, the types of problems that are there. Your job is to just really be the expert on it, the expert group on it. You got a question about it?
Oh, never mind.
But I'm going to put you in groups, and I know some of you probably, because of your schedules and that, work a little bit better together, but we'll just see for this first time how problematic it ends up. So, oops. What's it asking me? I thought you were asking me. Did I not just do that?
No, you have to click on it.
Oh, I'm up here now. Okay, already got that. Why is it asking the same question? Oh, got it. Okay, thanks. I lost my head there for a second. Let's see. Where is Christian? So it'll be Ashley and Colin right now. So go ahead and get with those people, and I mean, I don't care how you work. My suggestion might be figure out something that interests you guys. You probably have to do a little bit of research on your own. You may or may not be able to get together tomorrow. Hopefully you can at least. You know, you've got technology. You've got Skype. You've got FaceTime. Maybe come in early on Thursday, but something so in the end you will have something to get up and just, you know, show us what you found interesting in, just to get you guys, you know, interested in your education instead of me telling you, you know, stuff, because there's this much history. How much is important? You know, this much. Maybe none of it's important, but you don't have time to study all of it. So do that 5 to 10 minutes. That's it. It's not a formal presentation. It's get up. We found this interesting. Maybe I'd like to know more about this later. I might be able to put 2 or 3 cents in worth and that. So go ahead and get with those people right now, though, and get a game plan. Could be presenting a problem solution that you. The way that they wrote something. Let's see, actually following. No, that's right, Mitchell, we're missing Mitchell and Christian. So that's fine though, they're in different ones, so just do 2. Yeah. Yeah, I didn't see Mitchell in that. Yeah, I guess I didn't. That's fine. I'll give you 5 minutes and then I will probably come around and kind of see what your ideas are, what you're thinking.
you guys have an idea? I'm pretty curious about that. I don't, do you have
Yeah.
an
Yeah, I
idea?
think so.
Date,
What?
the Chinese.
You were gonna do that?
Yeah.
What?
Base 10.
Oh, but that's fine. If somebody else wants to do something like that, that's fine. But we'll see. Yeah, you know that's good. Somebody should present some of that. We'll try to stay away from all doing the same thing unless you have a different twist to it. One group is gonna show us the Babylonian symbols and how they wrote. Is that how you're gonna do something too? Okay, maybe Chinese. The Chinese. No, and that's fine because I think that I'm okay with two people presenting the same thing. I wouldn't want everybody, but just because there might be something new, different than that. So I'm okay with that.
I don't know. It's up to you.
We got problems with it.
Wait, you want my headphones?
No, I haven't used it.
So like, what do you want?
I find it fascinating.
Oh, my last recording. It was 3 quarters of the day when I took last Tuesday. So.
It's up to you. We don't have to do that. It was just an idea. Alright. What's your number? Yeah.
Yeah, no, it only goes into their history.
Oh, it's not on there.
It's
different versions. Call that.
how do you say it on?
We can provide pictures.
So do you want me to cover any of it and cover their symbols?
I got that a lot.
So you're just gonna search.
What a good map.
Yeah, just.
Yeah.
Don't worry.
Just two.
Yeah.
Here are the 15
Oh, it's only 9 chapters.
It's only 9 chapters.
Yeah, it's only 9 chapters of history complex.
What is it? What?
Well, it's just
But what is it? What are you looking at? What's only?
I just Googled low shoes.
Oh.
Early records or advanced.
But remember, just keep it to like what would have been ancient. You know, here, I'm sure things have changed, but just keep what.
triangles.
Yeah, I mean, you know, Wikipedia's certainly changed over the last
I know you used to be like a no.
5-10 years. But no, I mean mostly because now they're requiring references and you know, things like that.
We want to do the math.
Okay, the no shoe.
Yes.
Okay, make sure like don't when you're gonna do that, you know, obviously talk about some of its history, where it might have been first found and stuff like that too, and how you know how it's solved, different kinds. There's a lot of different ways to do things now.
Steve, I don't really know. Well, I already found this yesterday.
Okay.
I already commented on comments that said what the Egyptians
Probably.
Oh yeah, you were asking about like the actual.
No, he asked like what their use had.
Oh yeah. Oh, he asked that.
Yeah, and I found that they use cubits.
Yeah, the cubits, right? Span from here to here. Right. Okay.
Like, is there?
Present.
Is that what we're allowed to do that? Even though I already like talked about it.
Yeah. Yeah. No, that's.
And then I'm free from
No, it doesn't have to be anything. It doesn't have to be anything sophisticated. You know, I've got some things probably a little more mathematical and stuff like that that y'all do, but you know the goal here is for you guys to come up with stuff to study on your own and things like that. So I don't really have a set of. There's so much out there that I don't have a set of specific things for you to. I thought that was a good question. You know, people ask like, what do Do we know what other kinds of
Probably 3.
units they use? And, yeah, obviously, I mean, the cubit is a historical one.
Let's just say I guess.
And you could even in that, you could probably give a brief
12 at the mailroom. Okay.
history
No
of
idea where that.
like maybe why we do what we do even here, or something like that. How that advanced. I don't know. You might be able to find something if you're reading an article.
Measurements kind of.
Yeah. We measure why we do
Like downstairs?
what we do. I read something just the other day. It might even be this
The
morning.
24-hour.
Like,
That's over
just thinking, like, why do we have 360 degrees in something? In a circle, and it was making the argument that, okay, we get it from the Babylonians with the calendar, but maybe it wasn't just 360 days, because they used base 60, and then something to do with 12. Is that how it was? Something to do, yeah, something to do with 12, and then, yeah, but 12 times, because 12 times 60, so it would be half of that, right? And then, yeah, I can't remember exactly how it was, but it was just interesting how they argued, how they got the 360. So you might find something like that.
Yeah, we can do that.
You have to be proficient at writing the Chinese numerals too. No, I'm just kidding. You're gonna display them. I can't write Chinese.
What's your email? 85 38. That's the one.
So, for your Babylonian stuff though, not just the symbols, but you might be able to find some, possibly even like a video, I don't know, of people actually taking their little, because they would have taken a stylus and had clay and put it in, like maybe talk about like how they would have put it in the clay, and then they bake it. And then it would stay like that. You might be able to find some instrument symbols, like, or not instrument symbols, but instruments that would have been used to have that. It just been a stylus, like a little pen, and it would have had a little symbol there. And if they wanted to make a certain number, they'd put it in. And I mean, think about what that means if they made a mistake. They'd have to smooth it out.
They'd have just like a symbol.
Right.
And they would just say,
Well, right, and my understanding, some of the symbols were the same symbol, just tilted at a different angle to mean the same thing. But we have a pen, right? But they might have 5 styli. I don't know if that's the plural of stylus or not. But styluses, they might have 5 styluses, and as they're writing their numbers and doing their problems, they have to pick up a new one and put it in, to make the number, to make the symbols. Painstaking, but I mean, because we don't do a lot with tables now. If they do with tables, we say that, but I have no physics people in here now, but when I was going through physics and things like that, we have computers now that do all your calculus stuff. But I have one in my office, but it's a book of mathematical tables. And if I wanted to know a certain integral that looked like this integral, rather than typing it into a computer algebra system, I went to the book and said, okay, I have to match that up with this. Now, maybe I could have figured it out myself, or maybe not. Most of the ones that were that I needed were ones that I couldn't have sat there and figured out without 5 pages worth of work. And so what we do with tables is we match what we're trying to find out with what's in there, and then we just insert the numbers. Well, that's a lot for people to write those tables. Same thing that they were doing there. They were writing the table, they were creating the tables.
oh, good, it's just.
Today's on
Maybe put it in priorities so we can see.
Yeah.
It's a lot better than.
I was gonna say it's a lot better.
Yeah, I might do this. I go home and I feel good after that because I know what she was saying.
If I got actually taller, maybe. What's it now?
You know, I know.
And he's with me. But
Yeah.
I
And then you're still right for
Where are you education?
Shoot, I lied. I don't have. I wanted to show you a table, but I'm gonna get one from the library. I had a book of. I get one. The library has a bunch of books with math tables, and just when I think about people's painstaking, I mean they had slaves do it, but people's painstakingly, to create the tables.
I have a question.
What's that? Oh.
Why are there two different ways for input that?
Yeah, well, I mean, you might find different ways, because it could have possibly just been a different, like, method in a different area.
Or maybe, yeah.
This is what is it?
It's alright.
China's a big place, right? So, different areas might have had different,
Because on that one, the two is straight up and down, but then when they write like 924.
This thing kind of looks like a protractor.
Yeah, and some of it is development in there. This is the one I'm more familiar with. I mean, probably would know this one. Probably because these are obviously harder symbols, and maybe that's part of it. As you get here, you get harder symbols. In the end, it's not going to matter which one you really, use, because you'll find discrepancies in them because people are piecing it together.
But I still think
And I'm thinking it's cut at the end to where it's like a kind of like a line. And so like
that's
the
the only
single he just punches it in. And then he just turns it.
Did you find an example of doing something like that?
Doing something
These will be
at
on
the
tests like this, but different numbers.
he's like using it as
Is that claiming that it is? Okay, that one.
It's only gonna be everything.
So he's just making it up himself.
It's right here, so like, also,
Well, I guess that's all it would take, right? I mean, show us that video.
he should give you the hard.
Yeah, that would be all it take. You make a mistake, you want to do it again, smooth it out. But obviously, once you bake it, it's baked. You guys come up with something? Well, there are different. Well, there are different magic squares.
Oh, so like it's not on the Chinese one?
Well, no, right. I mean, I don't even know if you'll find specific information of like exactly how. Just because an ancient text has a square in there, a magic square, doesn't mean that it's ever been interpreted. I don't know if it has. Maybe find any of that information, like what was in the I Ching or whatever that was.
It confuses me.
But yeah, you can just show us. I mean, you can certainly show us different types of magic. But this is where it came from. You know what I'm saying? I mean, just like Sudoku puzzles and things like that. Those things usually have an ancient origin.
It was a picture, so.
And we think they're new, so we made them up, but they're actually, ancient.
Counting rises like 6,000. Write these again. Oh, did you really? Chinese counting. Yeah.
6 and that's 9.
I think this is still one.
Yeah, that's the 2.
And then plus 27.
Yeah, something like that.
So I'll just close here, and then I'll let you guys either stay in here for 10 minutes, kind of finish up, get a plan. A couple things taken away from today. People have always done algebra. I mean, since we know and have some written documentation, people have always done algebra. Hasn't always looked the same to us, just like that problem. That's what I kind of wanted you to take away from that. hasn't always looked the same. Methods haven't been the same. We've developed through thousands of years our system, our way of writing it. And we'll see as we get through the 1500s, we'll see, oh, there's a reason why we need to, I'm going to tell you the reason. There's a reason why we needed to develop a writing system of a better numeral system and unknowns, X's and Y's and things like that. And, you know, like I've said before, can't always divide everything up, you know, mathematically into certain time periods, but we can look at things that happened, you know, in this case before 600. Sometimes it can be messy and unclear, and speculation abounds, but just, you know, put things together as well as you can for something. It's a very short presentation, so again, I know you don't normally study yourself things because there's usually a certain amount of things that you have to learn, and then there's a test, and you know, so on and so forth. I don't worry about all that stuff. There's a lot of stuff out there with history of mathematics. I want us to learn some stuff, so I want you to take control of, you know, some of what you learn. I'll tell you some important things. I'll tell you what I know. I don't know everything, and you know, you figure out some things yourselves in little 5-10 minutes of talking to the rest of the class, telling them what you learned. So that's your main goal. You know, you have 2 hours of work to do, right, over the next, before we meet again. So you don't have much to do. Go back, look over the PowerPoint today, study those notes. Contribute to the D2L discussion that I mentioned yesterday. And then get your topic, and in 2 hours, you can study, meet with your person, talk to them over the phone, and 15 minutes before class, whatever, you can put together something and make sure that you are ready to share, you know, something with us for 5 or 10 minutes, okay?
Are we supposed to do a PowerPoint?
You don't have to. Oh, if that helps you organize things, that's fine.